So good evening, everyone. Thank you for joining us tonight for Nanotechnology Engineering Ask Me Anything webinar. My name is Kelsey and my pronouns are she, her, and I'm the undergrad recruitment coordinator for the Faculty of Engineering. So just a couple housekeeping items before we jump right in. So if you have any questions throughout the webinar, we do have the chat function disabled, so you are able to post those questions in the Q&A function. Those will be answered throughout the presentation, and we do hope to have a live Q&A session at the end of the webinar, so we can dive right into those questions and hear from all our experts. So if you have any questions throughout the entire webinar, please post it in the Q&A. If your question does not get answered in the webinar, or you have any questions after the webinar, if you could email us at enginfo@uwaterloo.ca, we would be more than happy to get back to you. There is also a closed captioning available under the little more dropdown if that is something that will help you tonight. So just click that more, languages and speech, and you can turn on our live captions. First, I am just going to give our territorial acknowledgement. So the University of Waterloo acknowledges that much of our work takes place on the traditional territory of the neutral Anishinaabe and Haunishone's people. Our main campus is situated on the Haldeman Tract, which is the land granted to the Six Nation that includes 6 miles on each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is coordinated within the Office of Indigenous Relations. You can visit native-land.ca to learn more about the land that you occupy. So to meet the experts that we have on our call tonight, you will hear from each one of them. We have Dr. Anna Klinkova, an associate professor and a Canadian research chair. We have a 3B current nano student, Amna. We are also joined by 2 alum. Sahad and Emma are also joining us as nanotechnology engineering alums. So you will hear from each of them tonight. So first, I'm going to pass it over to Dr. Anna Klinkova.
Hi, can you hear me?
Yes.
Okay, perfect. Thank you. It's my pleasure to introduce this program today. So I will talk about what nanotechnology engineering is. So just kind of basic definitions. Then I will talk about what our students study and what the environment is like, and just the program itself in terms of courses and directions that people can take, and also co-op streams, and basically all the opportunities that our students have. And then basically where they end up after graduation. So that is the brief overview here. So first I will start with kind of defining the point of this program. So that nanotechnology definition here is basically based on the scale of the objects and phenomena that we are focusing on in designing functional devices and functional solutions, functional materials. So here you can see the scale in nanometers. So you can find on the very right a human hair. So the thickness of the human hair is hundreds of thousands of nanometer. And when we talk about nanotechnology, we are considering the scale from 1 to 10 to 100 nanometers, basically. So where you see the transistors, or current transistors are 16 nanometers in size, or in that ballpark. So that is the size that is smaller than bacteria, smaller than the viruses, and much smaller than human cells. So it is approaching the size of the molecules. In fact, some macromolecules and biological molecules can be on the same scale as this transistor that is shown on this picture. So we basically are talking about the scale at which we are very much approaching molecular behavior. So that's where we need to study a lot of chemistry in this program. We're also studying electronic components. That is where it is a lot of kind of electrical and computer engineering aspects in this program, and also on that scale we observe very interesting physical phenomena. So that's why we study physics here, because we're basically capitalizing on this quantum effects that are present when you downscale objects to that size. And of course, it also is related to biological applications, because we're dealing with objects that are smaller than a human cell and the virus. So that is something that can actually interact with it, can be used for drug delivery and things like that. So basically, there's a big scope in terms of applications. And the unifying theme here is the scale and the phenomena and applications of this phenomena to functional devices. So it is small, very small scale, but has a very big impact because of all these emergent properties of these materials and these features on the scale. So if you think about materials, when you bring it down to that nanoscale, new properties emerge. For example, if you consider a piece of gold, you can think of a shiny metal, but if you bring it down to nanoscale, you can disperse nanoscale particles of gold in water, and they will be red in color or green in color or blue, different colors depending on the size of those gold particles. So this is kind of an illustration of how material properties change when you bring it down to that scale, and then how you can control, for example, optical properties and also electronic properties and so forth of the materials by changing their characteristics, such as size of particles and things like that. So that's what we use, for example, for sensing applications. So to become a nanoengineer, you need to learn the science aspects of that nanoscale world. You need to understand the engineering aspects of how to manipulate matter on that scale, and technology, that basically the applications where all of these materials and phenomena on nanoscale can be applied to solving some real world problems. So this program is recognized by the professional engineers of Ontario, and basically this is an engineering program. So the main thing you're focusing on is solving problems. So you're learning the science of nano world to solve problems and make useful devices and address various challenges that our society faces. So to kind of bring together different aspects from smaller than nano, so molecular world, and also from the larger scale, you need to learn chemistry and biology for various biological applications and sensing, things like this. Also, you need to learn physics and electronics because we're capitalizing on the properties of materials that are in the quantum realm. So that is where we have to use some of those new emergent properties, but also account for them when we, for example, do further miniaturization of electronic components. So once you bring all of those transistors down in size in your cell phone, for example, at some point you're running into this quantum phenomena that are not accounted for initially. So you actually need to make sure that you take care of them in order for your device to function as intended, on one hand. On the other hand, you actually can again use those emergent quantum phenomena to build things like qubits for quantum computers. So all of those aspects are part of nanotechnology and a part of what we're learning in this program. So this is an illustration of how nanotechnology can be used in real world, and I will show a couple of things that are completely from different realms. So this is bio applications of nanotechnology in combating COVID-19. So everybody has heard of mRNA vaccine, but there is a nanotechnology aspect that allows delivering this vaccine to the parts of the cells where they need to be. So that is basically a self-assembled lipid structure. It's on the nanoscale. It's the nano-size structure that contains within this drug molecule, and that's what gets essentially released once it enters body where it needs to be. So this is where therapeutic applications of nanotechnology, that's just one of the illustrations, but many others exist. So some of those things can be used for diagnostics and therapeutics at the same time. So that's theranostics applications of nanotechnology. You can also use various nanoscale systems for sensing applications for both bio species and also things like, for example, air and water pollutants. So this is also something that we can do with nanotechnology when it concerns biological aspects. So on the other hand, we can make integrated circuits using nano features, and this is a very big domain of nanotechnology. This is basically the heart of your cell phone and all electronic components, a computer and so on. So if you consider a memory card or other components in your cell phone, they're very tiny, but they contain trillions of components, and they contain billions of transistors. And so how do you fit them all on that very small size? So this is where nanofabrication comes in. So this is what we can do in a clean room. Basically, we can fabricate layered structures that contain all of those components, and it's that fabrication is what enables all the electronic applications. And so we have a unique ability to train you in clean rooms, because we are the only program in Canada that actually has clean room training labs for undergraduate students. So usually this is something that students learn in their graduate programs or when they actually work for companies. It's kind of extra training, but here at Waterloo, you can study this during your undergraduate training. So this is because we have designated clean rooms. So this is basically, first I'm just going to show you what you make in a clean room, and then there will be a few pictures of what our clean rooms look like. So this is a wafer that contains a large number of individual chips. So in this case, it could be hundreds of thousands, depending on the type of chip that you're making. And if you consider that one chip is worth $200, a wafer like this can be worth hundreds of thousands of dollars. And how do you make it in a clean room? So the main feature here is that because you're making it all at once, all those hundreds of transistors are produced in one go, because you're integrating those layers on the transistor. There's specific design, electronic design, and then there is a specific implementation of these components physically, because you actually need to be able to grow them without defects. You have to modify it and make sure that all the components are functioning properly, and consider that all the features here are smaller than much smaller than a human hair, so much smaller than a piece of dust. So you really have to have the environment that is completely dust-free. There is nothing that can contaminate it. So that's why we need a very special environments for making these devices. That's what clean rooms are, and that's basically a room which is completely free of dust. You can also see that there is a special yellow light that clean rooms usually have, because the components that are deposited there, they are light sensitive, so they're usually cured with UV light. So just to make sure that they are not affected when it's not intended. The light generally is yellow, and then it's specifically illuminated. The components are illuminated with UV light to cure something. So basically, that's a very specific environment, and that's on one hand just the space that needs to be very dust-free and high purity, and you have to have a certain attire to enter such environments. So this is the training that you will have in terms of in terms of this lab, but also it has all the equipment, very specific designated equipment that you will be learning how to use in order to fabricate devices. So that there are some sample devices that you'll be able to make, and you will go through the whole stage of fabrication. So you will know all that it entails. And of course, when you are fabricating something more sophisticated, you're going to learn about the extensions of these techniques, but all the basics you will know as a part of your basic training in the program. So this is our big feature in terms of hand-on learning experience. This includes the clean room, and there are a couple of pictures here. So you see kind of just a glimpse of what it looks like. There are specific equipments such as chemical vapor deposition. So that's where you can deposit various components on those wafers. And this is a plasma enhanced one. So this is what you can use to do those depositions at lower temperatures, at milder conditions. There are also physical vapor deposition instruments. So there are basically different ways. One of them is physical evaporation and deposition of metals and other components, and chemical vapor deposition. Basically, you're doing at the same time some reactions, so you're evaporating some precursors, and then you're depositing what results from the reaction. So you need to know not only the physical aspects of it, but also chemistry and what can occur with those compounds as they react. That's why chemistry is a big part of this program. So here you can see some of the clean room pictures where the yellow light is required. So that's where the developments are done. So you can see that those are units where photoresist process. So those are the chemicals that are sensitive to light. That's why the light is yellow. And so you have this UV exposure tool where you can cure those photoresists. Then once you fabricate these devices, you need to know what you actually made, and you need to confirm that your design was indeed implemented. And we're talking about very tiny components. So this type of structures, those nanoscale structures, are not possible to image with an optical microscope because optical microscope has a certain physical limitation, and you cannot really go below 200 nanometers with an optical microscope because that's the optical limit. So instead, you need to image the samples with an electron microscope. So instead of light, you're using an electron beam to visualize what your sample looks like. So scanning electron microscope is one type of the electron microscopy techniques that can be used for characterization of nanoscale materials. And so that is, we have a designated unit that is specifically for the program for training. And of course, we have plenty of other instruments on campus as well. So our students can get exposed to it through other experiences, such as research experiences with our research groups. But in terms of just the basic training, we're starting with this electron microscope where people can characterize their own samples, and then they can use it while they're doing their capstone project, for example. So this is the instrument with the standard access. We also have nanoelectronics laboratory. So that's the advanced lab where you can do microprobing. You can basically make various devices. It could be specific chips. It could be also sensors. So, for example, optical sensors. So we have optical spectrometers to characterize the material. So there is a full range of instruments to experiment with different device fabrication for electronic and sensing applications. So the materials laboratory also is a kind of a very, very important component of our portfolio of labs in this program. So this is where you can make various materials, and that's where we're talking about making them basically from bottom up. So this is not like nanofabrication where it's more of a kind of layer by layer formation on a wafer. In this case, you're going to be making something in a flask, more likely, but you can also make solid state materials. But you're doing a lot of molecular chemistry to synthesize various polymer nanomaterials, carbon nanotubes, and things like that. There is some parts of battery research as well. Because contemporary batteries, they include those components of nanomaterials that enable their fast performance, for example. So that's all that you can do in this basically wet chemistry lab. So again, this is a fully equipped facility to get this initial skills. And then, of course, you can further have more experience through your co-op terms and through working with research groups on campus. We also have 3D printing facilities. So, for example, if you develop polymers, polymer nanomaterials, you can then use them to 3D print certain prototypes. So you can actually make nanomaterials and then make things from them. So various actual geometries and integrated into some devices as well. So that's again something that is directly accessible in our spaces. So with all of this, you have a full range of training in various areas, and then I will touch on how you can specialize in later years. But with this experience, you open the door for many applications and many industries. So the majority of our graduates end up working in industry, mostly based on their co-op experiences. So that's kind of what guides them to decide what they want to pursue as a career specifically. But many students also continue their further education in academia. So there is an opportunity to do co-ops in academia. So some people do some research during their co-op terms, and if they like it, they can continue with graduate school as well. So many people do this kind of mixed co-ops with industry and academia. And as you can see here, 8% of our students end up working for startups. And often it is the startups that they actually founded themselves. So that is usually based on their capstone project that they do in the final years. So that is something that they work as a team for students. If it is a successful device, a successful design, they can actually try to make it a commercial success, and so that's where startups segment is from, and also some of them just work for startups as part of their co-ops and then find placements there after graduation. In terms of the sector, you can see here that lots of people work in semiconductor industry and healthcare. So those are for the reasons I've shown those initial examples for. So many people also work in software and IT. So there is a lot of training that is actually a translatable set of skills for that industry as well. Manufacturing, this is usually related to nano materials. Mining and energy also related to that. Many people work in the battery section afterwards, and so you can see that there are a variety of other avenues to explore as well because of the diversity of the experience that people have in this program. So when you start here, the first 2 years are pretty fixed in terms of the courses. So you move through the program as a cohort, taking classes together. So first you learn about the engineering practice, you do all the introductory foundational courses like programming, chemical principles, algebra. You also learn about environmental impacts of nanotechnology to be responsible citizens as you do engineering practice. You also learn physics, again, foundational physics for nanotechnology engineering. So that's where you learn about all the quantum effects that can be present there and just properties of materials in other ways. And an introduction to material science. This is basically all the foundation for upper year courses. And then the second year, you continue with that. So that's where you learn kind of advanced courses such as it's not really here, but such as organic chemistry, and so basically there are some upper, more advanced versions of all of this directions. So chemistry, electrical engineering, physics. So those are the aspects that you learn. You can see here that there are some options as well, but this is usually what you are considering in the upper years. Basically, in your third year, you decide one of 4 concentrations. So that is micro and nano instrumentation. So that's more related to making various sensors and for target applications. Could be biosensors, it could be environmental sensors, and so on. Nanoelectronics, which is more related to chip fabrication. Nanobiosystems, this is more related to drug delivery and things like that. Nanoengineering materials. So this is a very broad application scope, but this is where you work specifically with new materials, emergent properties, and then the application sector could be varied in this case. So this is where you, based on your concentration, you can choose courses based on your interest, then you can also have some options with additional courses that kind of complement those directions. But we do not have a minor specifically because this program is quite dense in terms of the course load. So in terms of the co-op distribution, this program is a co-op program, so it's not an option. You only have the co-op version, so that's where you do 2 4-month co-ops in the first and second year, and in the third and fourth year you have 8-month co-ops. So this is how you can get some industry or research experience in your first 2 years while you're still getting all the basic training, and that's what helps you determine your specialization. And so you can try 2 different sectors before you decide what works better for you, and that's how you can kind of do the self-discovery in terms of your professional path. And in the third year, as you specialize, you can again do co-ops based on your target area of where you would like to find a job in the end. And so that's you can also decide to do a mix of industrial and academic co-op to decide whether you want to pursue further education. And so that's what usually people do. And basically, depending on where you're at, and it kind of evolves as you go through this program, you learn more, and you'll find out about opportunities that you haven't thought of initially. And so that's kind of what leads you through the scope experiences. And in the end, you have 2 years of work experience as you graduate from this program in the 5th year. And with this, I would like to pass the mic to the actual students in this program who can share their experience as they've got through. And so this I think would be very informative for those who are interested in this program.
Yeah, hello. My name is Amna. I'm a 3B nano engineering student, so I'm a class of 2026. And then I guess I'll speak a bit about my co-op experience. So my very first co-op, it's usually a bit harder to get your first one because you're just fresh out of high school and you don't really have as much experience. But my first one was working as an electrical engineering assistant at TTC, so Toronto Transit Commission. And I got to do a lot of engineering drafting drawings and using like AutoCAD and CAD software to draw up electrical power systems. I even got a chance to do some field work and visit construction sites and do resistance tests and making sure that power rails as they were being constructed were conductive, so that was cool. And then I very quickly realized that electronics was not my thing and got more into nanobiosystems. And so that kind of carries through the rest of my co-op. So my very second one, I actually worked here at the University of Waterloo as a research assistant in a research lab that was looking at virus and complex biology. And what I got to do is I worked with a PhD student where we used microfluidic devices to grow and model bacteria cells and be able to create mathematical models of how they grow and how they infect each other. And this was to study antibiotic resistance. So that was a lot of fun. I got to fabricate the microfluidic devices and then actually implement them and use them. So that's what that picture right there is. You see two different types of bacterial cells, and then we would image them over time to see how they grow. My next co-op was my first 8-month co-op. And I worked as a medical research assistant, so in a hospital setting in Toronto at Princess Margaret Cancer Center. So this was a genomics lab, so I got to do a lot of biological characterization and genomic work, which was really cool. I got to work with drug trials and clinical trials in the hospital and kind of see what a more faster paced environment was like. I also got a chance here to do my own solo research project. So I brought in the nano to a job that wasn't necessarily nano related. So that this lab used to do a lot of in vitro work of making tumor models with 3D in vitro studies. And so I, in my solo project, brought in carbon nanotubes as a scaffolding to improve the efficiency of their in vitro models, which was a lot of fun. And then being in my 3B term right now, upcoming in the next semester, I have my last 8 months of co-op. And so I've luckily arranged a job and will be working as a microfluidic systems engineer at a company that does point of care blood testing. So here they use microfluidics to test blood much faster than you would if you actually took a blood sample and then sent it to a lab and had to wait for your results to come back. So that's kind of co-op experience I have going on right now. And then what I love about nanotech. My most favorite part is the amount of cool stuff we get to do. There's a lot of hands-on lab experience, and that's kind of right away from first year. You get to do a lot of labs every single term. And then some of the cool ones that they always hype up and you hear about from first year is being able to make quantum dots, which you make in your 3A term. And they're really cool because you make them in different sizes, and size determines their fluorescence properties. So that was a lot of fun. And then recently, I also got my chance to work in the clean room. So, like Professor Klinkova was talking about a second ago, we made our capacitors, and you just layer by layer build up your devices. That was a lot of fun. Another really nice thing about Nano is that there's a really strong community, both with the profs and then the classes itself. Because of the cohort system, you're with the same people all day, every day until you graduate. And so you very quickly get a really nice support system and you're doing everything together and you have friends with you along the way. So that's really fun. And then my other really favorite thing about Nano is that the applications are endless. Nano can branch into so many different fields. You could do biological work, you could go into electronics, you could do energy storage. There's just so many different ways you can implement nano, and the applications you don't even realize they're there until you start looking into it. So I think that's really cool. It's very multidisciplinary. Yeah.
Hi, everyone. My name is Sahad Basanji. I graduated from Nano in the class of 2022, and I recently finished a master's also at Waterloo in the chemical engineering department. So to talk about my co-op experience, first I chose Nano because there wasn't really a program at Waterloo at the time that covered a little bit of everything. Like I wanted some biology and I wanted some physics, and the biomed program was still very new at the time. And funny enough, the nano program actually had more bio. So I had chosen, well, at least I ended up on nano of all programs. So my first co-op was as a quality engineer with a medical device startup. Basically, they made very fancy brace wires where instead of, I guess if you can imagine like Invisalign or braces, you have to sometimes get 2 or 3 of those retainers or brace wires that are changed out. They basically create a special wire where you'd only really need 1 brace wire and for the course of your whole treatment. So my work was very material science heavy. It was working with basically the alloys that they would make the brace wires out of and helping to speed up production. This lended really well into my second year materials lab, like the course that we do in our second year. So that was kind of nice. I had also found it through Waterloo Works. My second co-op was at the Japanese National Institute for Material Science. I found that through a talk on campus where basically a prof came to give a explanation of their research. And what that work involved was basically the lab had created a bionic nose. So if you imagine Android robots, they can typically see, they can typically hear, and they can typically have a sense of touch, like they can feel things, but they don't really have a sense of taste or the ability to smell things. And that's because those 2 senses are more difficult to replicate. So with this bionic nose, I was helping out in terms of expanding the library of things that they smell. So for example, they could detect cancer, they could detect if an apple was rotten or fresh. And so that involved a lot of polymer chemistry and a lot of coatings. I got to use some pretty fancy equipment. And it was nice to, I guess, be in Japan and be able to explore. So the image on the top right-hand corner is actually a schematic of how it works. And basically when a vapor comes onto the sensor mechanically deforms, as seen on the right image. So the third co-op I found through Waterloo Works, and this was at Harvard University. What we had developed was a system that could be used as like a smart window where I'm sure you've seen blinds open and close depending on if it's too hot or too cold or based on the light intensity in smart buildings. So this was kind of, this is similar to that, where imagine the window, instead of having blinds, the window would get opaque or transparent depending on what temperature was without the use of electricity. And so in that work, I was basically tasked with determining the feasibility of if it could actually be integrated into buildings and work at room temperature. So this was a lot of mechanical design, a lot of machining, a lot of analytical chemistry, like the machines that we would learn how to use in our second year labs. And also, Professor Klinkova mentioned about the semiconductor and the clean rooms. I was able to actually use some there as well. And that was in Boston, so it was fun to, I guess, experience that environment outside of Waterloo. My last co-op was at Waterloo. So this I had found through LinkedIn. And basically, there was a new professor that started at Waterloo who designed medical robots, kind of like the Magic School Bus, where I don't know if you remember that episode where it swims into that student's knee and is able to traverse and travel the bloodstream. Those kind of medical robots. So because he was brand new, like he had just started, basically I had to set up and basically build his lab up from scratch, from the electrical work to the equipment installation to starting on the research. So that was a very fun experience of, I guess, understanding the behind the scenes of what actually do you need to work in a safe lab and to have a lab that does everything you need it to do. So I want to now chat a bit about, well, what's so great about nanoengineering and build on what Amna's talked about. I mentioned that I wanted to do nano because it covered a little bit of everything. And this is just a short list of some of the classes that overlap with the other departments. So not only are you building a specialization in your own niche in nanotechnology and nanosciences, you also have the ability to speak on the wavelength with mechatronic engineers or chemical engineers or mechanical engineers. You're also able to go into a lot of different careers, not just within nano, as Amina mentioned, but also outside of nano. I've had friends that have tailored all their co-ops in software. They've done a mix of robotics. They've done various consulting and project management gigs. Some work for like electrical design companies now, and others have gone the pharmaceutical route. The diversity of preferences is also really nice because you get to see the different kinds of things they work on and experience the different teaching styles. This is just a short list of some of the departments that we have professors from. And last but not least, if perhaps you like school, this sets you up very, very well for graduate school, regardless of what kind of graduate degree you choose. I, for example, chose a master's research-based degree. I've had friends go into medical school, law school, and business school, and they've all said that it was an easier experience than their nano degree, which is, I think, something interesting to say. And yeah, nano really teaches you how to learn a lot of different things. So that's why you're able to succeed, whether you choose to go to the industry or go to any of these different graduate programs. So I'll turn it over to Emma for the rest of the presentation.
Okay, thank you, Sahad, for the introduction. My name is Emma, and my pronouns are she, her. And I know we've kind of been alluding to this other side of nanotechnology and the variety, and I'm maybe an example of the variety. So I currently work as a technical project manager at a biotechnology startup based in Waterloo. So still very involved in the alumni community. And I just graduated this year, about 6 months ago. So just entered the industry recently. I'll jump right into my co-op experiences. So some examples here would be, I started kind of in ops, so doing more troubleshooting and process-driven work. Specifically got into the startup scene quickly. I have some family that I've grown up around that's in startups, and I think like that's an environment that fits me really well, and it's what I've continued with as I've graduated. Having a lot of ownership is really important to me. So started working at that robotics startup. It was larger scale robots that did field work. So working with the engineers, like the electrical and mechanical engineers, to create those engineering processes and translating it up to people as high as the CEO at that time. Next, I went to Bombardier Aerospace, which is, again, a very different engineering field. And that was a manufacturing space. And since then, I've kind of continued to be interested in the manufacturing experience and process. It's really important in a lot of companies. And it's great to get exposure to that early in your career. So I was working in the project management office at Bombardier on their like internal operations team, specifically on the Global 7500, which a fun fact I like to tell people is that's the private jet that Kylie Jenner has. It's their highest selling jet. So getting to see the environment and what it takes to create something as big as a plane, obviously very opposite to nano, but a great way to throw yourself into a whole new environment. So working with people on the floor on a day-to-day basis, all the way up to GM level people that are coming to do quick run bys. So this role is where I really learned my ability to translate from low-level technical information from my degree background all the way up to business level information. And that's kind of what's defined where I've taken my degree post-grad as well. Next role, went back to a robotics startup. I am a hardware girl till I die, I guess. So this was probably the most nano role I did. This startup did force sensing. So I know Sahad was talking about those Android robots. So for example, one of the sensors they created was a touch sensor for fingers. They did some work with surgical robots as well. They also did more like industrial manufacturing robots. So that was one of the projects I was on. So I was project managing more of a client-facing role at that company for a top 5 company. And it was really awesome. I got to go on site, see the sensor integrated into the robot, drive around. And that was an amazing experience to see the engineering work that I had been involved in at the company go straight into the product for that company. And then my most recent co-op before postgrad, obviously, was working at Ecobee. You may know them for their thermostat business, but I was more in the sensor space and camera space there. So they just released a doorbell camera about a year ago, and I was there for the 2 or 3 months post-launch for that co-op. and basically was taking the customer and user feedback in their trusted circles and implementing it into features before launch. So working with the hardware engineers, firmware engineers, software engineers to get the product ready. Okay, jumping back into the nanosphere. Some of my points are a little similar, but I'll try to put my own spin on them. So of course, the people is something we've talked about a couple of times already. Honestly, I would put a gold star on best professors at maybe any university and maybe at Waterloo. People love doing nano. It's fun, it's innovative. The class has that energy as well. I can genuinely say I knew every single classmate. I think our class was about 100 people. I knew everyone's name, felt like I could say hi to anyone walking in or sit next to anyone. I attached a little photo here of our ultimate Frisbee team that we had in our first term. We were called the Carbon Nano Dudes, which is a pun on carbon nanotubes, of course. We continued the intramural teams throughout, which I think is really important, having that class community to get through it together. Like any engineering program, it's a really tough program. I know Anna touched on that quite a bit. And although it's tricky, having that camaraderie was really amazing. My next point, another little pun, is putting the SC and BASC. The lab experiences are nothing like you'll get at in any other engineering program because of that collaboration with the science department. So access to millions of dollars of equipment, being able to use them from first year. I learned how to do so many different lab skills and then be able to implement them in our own project in capstone. I've attached a photo here of me with my capstone group, who are a bunch of awesome women in engineering. And this is us using a plasma chamber to make a microfluidic chip for a blood testing device. So similar to what Amna's doing for her co-op, actually. So that's us working on that with some really fancy equipment. And then something I know the other speakers talked on as well is the ability to access so many fields. I think when people hear nano, they think it's really specific, but it actually gives you access to so many different industries. So some of my colleagues or classmates went more into hardware engineering and started taking more ECE related courses towards their upper years. Others focused really hard in on software and simulations even. We have some courses for that as well. Chemical engineering, you could go more into things like ecology. Biomedical, you can do more biomechanics and again, maybe more technical or mechanical work as well. So the ability to access all those different fields and also getting the background in your early years to do that is something really unique about nano in my experience. And that gives you so many options when you come to graduate, where you could have someone doing a master's like Zahad, to me, who's in industry doing PM work, in just an example of 3 nano students.
Awesome. Thank you so much, everyone. That was a lot of information, but I think it was really valuable. So just a couple things here before I kind of go through these questions and ask some of them to our guests here. So if you do have any questions after this presentation, you can always email us at enginfo@uwaterloo.ca. I'd also recommend visiting us for a tour or our events. We did just recently have our fall open house, but we will have our March open house on Saturday, March 22nd. So keep an eye on our website to register for our upcoming open house. I would also recommend, if anyone wants to chat with a current engineering student outside of this webinar, you can visit that website there and you can live chat with some of our current engineering students. We have numerous ambassadors on our platform in multiple programs, so you can message them any questions you have or set up a video call with them, which is a great way to kind of get that student experience and really get those questions answered. But I will ask all my guests to turn their cameras on. And I'm going to kind of go through some of the questions in the chat here. So I saw there were some questions about specializations and options. So I just wanted to touch on that quickly. I know Anna mentioned there are 4 specializations. So the biosystems, electronics, fabrication, and materials would be those upper year specializations in nano. And we also have options in engineering, which are similar to a minor, but a little more engineering based. So we have a long list of those. So we have biomechanics, computer engineering, entrepreneurship, mechatronics, couple other options I'll post in the chat for you guys to see. Let's see here. Now, there was some questions about, is it difficult getting your first co-op? I know you guys all talked about co-op, but if you wanted to, if anyone struggled or anything with their first co-op, do you want to talk about your experience getting your first one?
I can maybe share a little bit more. I didn't share this in my slide. My first co-op was actually in winter. Well, I was applying in winter 2020, so COVID impacted my first experience. I think building a strong resume before, like if you're accepted before you get in over the summer is really valuable, even if you're in Stream 8 like Nano. Getting many eyes on it. We have lots of resume critiques. I was really involved with Engineering Society, and they run those. So you can get lots of help with that as well, or even like help navigating Waterloo Works for the first time. So for me, losing that co-op was difficult, but had that help and support through my networks when applying for my next one, which then led me down the career path I'm on now. So.
Thanks.
I also can add a little bit, because indeed the first one is a bit hard because you don't have experience, and when you apply for the second one, you already have something on your resume to show that you've you have hands-on lab experience and things like that. So that's where a good thing to know is that we have so many research labs on campus. So it's a great variety of choices in terms of what kind of exposure, what kind of experience you can get, and it's just a matter of being proactive and reaching out to professors as well. And so that's where you can get your first co-op if you're a little bit intimidated by going into industry the first time, and then maybe the second co-op. Again, you can have some connections with industry, even through your peer group. So and also our co-op office provides a lot of support. But again, that's just something for kind of to know about the options. There are lots of options on campus if you find it hard to find it anywhere else for the first one. And I think that for the second co-op, it's much easier than to find it than for the beginning.
Thank you. Someone was asking about your schedule. Do you choose or make up your schedule, and do you get more electives in your upper years?
Yeah, so the nice thing about engineering here is that you don't need to pick your schedule or like do that thing where you race to your computer and try to enroll into classes. Because it's a cohort system, you'll take all your classes are predetermined by the registrar's office, so there'll be a set schedule that you follow. And then once you get to your upper years, then you have to start picking your technical electives and your complementary study electives. That's when you actually have to enroll and pick. But I think the first time you do that is in second year in 2A when you need to pick an English elective. And then after that, it's third and fourth year when you start picking your specialization courses and your technical electives. But first year, you just show up and you get your class schedule and it's ready to go for you.
Maybe I can also comment on this question about the difference between materials science program, because we happen to have that one as well at Waterloo. We have nanotechnology engineering, and we also have materials and nanoscience. So the focus is a bit different in terms of where your passion lies. So with the NE program that we're talking about here, the primary focus is on solving problems, making some functional devices. So basically, it's the application-driven kind of mindset. Whereas for materials and nanosciences program, the focus is mostly on understanding the underlying phenomena. So it's more about asking the questions of why things work the way they do, than how to how to make something work, which is more of a question of engineering. So it's kind of it depends on where your passions lie, and we have both of those programs, and they are excellent. And so materials and nanoscience is between physics and chemistry, and nanotechnology engineering is between chemical engineering, electrical and computer engineering, and chemistry.
Thank you. Let's see here. Well, there's a question about Waterloo Works. So Waterloo Works is an internal job board that we have here at Waterloo, with a whole bunch of jobs listed. I know, Sahad, you mentioned that you went Waterloo Works or externally. Did anyone else kind of use Waterloo Works or contact their own companies, or did you all kind of use Waterloo Works for your co-ops?
I put it in the comments as well, but I use Waterloo Works for all of my co-ops. I think if you're looking for a specific location, like if you're targeting going abroad somewhere, it's a bit more difficult, of course. I wanted to stay more in the GTA or tri-state, like Tri-City area. So in general, I found everything I was looking for there. And I also wasn't hunting for like a specific big name company. So I think it's a little easier depending on exactly what you're looking for. If you want to go outside Waterloo Works, but at least for me, I was pretty open to roles that are at a lot of different kinds of engineering companies, and that's just my field, so it lended itself better to that job board.
Yeah, I also got all of my jobs through Waterloo Works, but I wanted to mention that this past semester Waterloo Works kind of got revamped, and so there's actually two separate job posting boards within the system. So you have what has always been there, where you have direct a rank match system where you apply to a bunch of jobs and then you go through an interview process and then you get ranked and matched with your employer. But they also have a separate board where you can directly communicate with employers. So it's similar to finding a job outside of Waterloo Works, except they've kind of folded it into the infrastructure of only needing to use one platform to do so, which is really nice and makes job hunting a lot faster and easier.
Awesome. All right, it's just about 9 o'clock. Did any of you have any last minute things to say to everyone applying to nano engineering?
I maybe have a tidbit I can share. I know Sahad mentioned his consideration of BME as well, but I know lots of people considering doing nano are also thinking about biomedical engineering. I did a shadow day when I was in grade 12, which is an amazing program. I believe it's still running, I hope. But I shadowed a nano student, and BME was my first choice, and then I got matched with nano. And from the day I did that, I knew I was doing nano. I knew I was applying for it. I never even thought about BME again. So if that says anything about the culture or how it is, I hope that convinces you. Obviously, still look into all your options, but yeah, maybe just a little tidbit about how I feel about my program. I'm very proud of being a nano student. It was awesome. So.
Thanks.
I guess just adding on to Emma, I also did the shadow day, and yeah, I was in the same boat where the whole nano experience kind of really changed my perspective. If you're someone that uses the internet like Reddit or other things for figuring out what programs they want to do, take the stuff about nano with a grain of salt. I don't think a lot of people fully understand nano until they're really in the thick of the weeds. I know at least I didn't. And so, yeah, it's a really good program in the sense of you get to take the biggest diversity of classes of any engineering program in Waterloo. And I don't mean that as like a bias statement. I mean, like if you look at all the other programs and see the diversity of classes for subjects, there's that. So if that is something that interests you or you're on the fence of, between two programs, that could be something to consider as well. So yeah, best of luck in your search. And I guess if you have more questions, feel free to reach out to me on LinkedIn or something.
Awesome. All right. Well, it is 9 o'clock, so we'll wrap up. So thank you very much to all of our experts and our speakers. Thank you to our alum for coming back and speaking to all the students. I see we answered a lot of the questions, I think all of them in the chat. Again, if you do have any questions, please feel free to reach out. Also visit our website. I posted the link in there for our Shadow Day program. It is still on, but our students are about to go right into exams. So we'll be back open in January. We'll start booking those in. But if you have any questions, please reach out. But if not, I hope everyone has a great night and thanks for coming.